Greetings. As I'm recording this screencast, I'm battling a bit of a cold. My voice is a bit weak. Hopefully that won't be a problem. In the last chapter, chapter 11, we studied gases. And with gases, we didn't really have to worry about intermolecular forces, except under super high pressure or super low temperature. But with liquids, we do. Now, this chapter is more about how liquids come to be as opposed to the properties of liquids and of fluids. In AP Physics, a whole chapter is dedicated to fluids and the movement of air and water and fluids from one place to another. Here we're just looking at the fact that in order for there to be a liquid, there have to be forces of attraction between the particles that will attract the particles together and keep them that way. That's true for both liquids and solids. It's not true for gases. So whenever we study melting points, which would be the same as a freezing point for a pure substance, or the boiling point, which would be the same as a condensing point for a pure substance, we are interested in these intermolecular forces in order to understand why that melting or boiling point is low or high or somewhere in between. And we're going to begin our study by looking at creation and considering the gecko. Now, you thought that the gecko was just the main critter that is advertising car insurance and other kinds of insurance on commercials. But geckos are pretty remarkable creatures. They can walk up walls. They can walk across ceilings upside down. They seem to defy gravity. And how is it possible for them to do that? Well, of course, in science, you observe something in nature, and you're curious. How do I explain that? What's going on here? Your motivation might be to see if there's a practical application. Your motivation might just be straight curiosity. So we move from the wonder of the observation to the curiosity to asking questions to doing some science to try to answer those questions. And along the way, we have to make all kinds of observations with our instrumentation. So when we observe the feet of the gecko, here's a close-up, we see that they have these stiff hair-like structures called setae. AE, right here, is a plural ending in the Latin language. And these are about as long as the thickness of a human hair, which is 1/10 of a millimeter. And you've got thousands of these things on pads. And the pads are called this, and there's another Latin plural ending. And these are about 200 nanometers wide, which is smaller than the wavelength of visible light. Give you a sense of how extremely small they are. Now, your textbook, the authors of your textbook, use the word design here and the word design there. And when you study creation, you almost can't help but use the word design because it doesn't look like something that could be cobbled together by pure accident and chance and random mutations over however much time you want to give it to create something so remarkable. After all, if you think about it, if it's going to take many, many, many scientists, perhaps hundreds of scientists, working over combined hundreds of years, using fancy equipment invented by hundreds of other scientists over many years, in order to begin to understand how something like a gecko can walk across the ceiling of your house, you realize that it took an awful lot of intelligence to discern this. And the inference to the best explanation is that the reason we can't avoid using the word design is because it was designed. The reason we can't avoid using the word design is because it would be ridiculous to think that random mutations in the genetic code, and course, you have to ask the question, where did the genetic code come from in the first place? Over many, 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 many generations, could produce such a thing. How many mutations does it take to give a gecko the ability to walk across the ceiling? And you see that sounds very far-fetched and very imaginary. But of course, once you rule out a designer, once you begin with a prejudice against there being a God, you're very limited in your options to explain this kind of thing. There is so much that you can learn about intelligent design, that resources available online. And I would suggest, if you want to know more, you go to the Discovery Institute. And I had the privilege one summer of studying out at the Discovery Institute. This organization focuses on design because they believe in a designer. Most of the members of this institute and the professors and the researchers are Christians, though there are some that are agnostics from many different faith backgrounds, but they all recognize the inability of any type of Darwinian evolution or materialistic, naturalistic process to produce these kinds of things. So discerning that which can happen by accident and chance from that which cannot happen by accident and chance is a field of research. For example, if you go out to Utah and you look at one of those natural arches that wind and erosion has carved out, you know it's an arch, and it looks very interesting, and people travel great distances to see it, and I've even walked across the surface of an arch. But the top of an arch out in Utah, but it doesn't really do anything other than being something amazing to look at. But if you go down to St. Louis and you look at the arch down by the river, no one would think that happened by accident and chance. No one would think that was carved out by wind and rain and erosion and so forth. In fact, even just looking at the outside, you know that this was designed. And then when you go inside, you see design upon design upon design, intentionality. You see a mind. You see rationality in how that was put together and laid out. So the Discovery Institute is a great place to go for resources. All right, let's continue on. The way in which a gecko was able to do that is because those thousands and thousands of very, very fine hair-like structures that are on the pads of the feet are such that they can have very, very, very close, intimate connection at the molecular level with the molecules that make up the surface that they're walking across. Excuse me. And because of those intermolecular attractions that we're going to be talking about, that force of attraction between the thousands and thousands of setae on the spatulae of all the different fingers, if you will, of each of the feet of the gecko produces an intermolecular force in total that is greater than the force of weight due to gravity that would cause the gecko to fall down. So, the intermolecular forces are called van der Waals forces after a Dutch person. Van der Waals forces. And you can think, when you come down to this last paragraph, once we understand this, we can begin to say, I wonder if we can put that to use. I wonder if we can come up with remarkable adhesives, which is a huge field of research. Imagine decades ago where you didn't have Scotch tape or masking tape or painter's tape, or even all the different kinds of glues that we have now. So when we go into nature, when we look to creation and try to find some structure that we want to imitate or copy, that field of research is called biomimetics, or it's called biomimicry. Biomimicry. I think I spelled that right. All right, let's get into the chapter. As I already said, the only time we had to worry about intermolecular forces, IMF, as far as gases are concerned, was when we had a non-ideal gas. And when you have tremendous pressure and cold temperatures, the collisions and the proximity of the particles to each other necessitates us taking into consideration these intermolecular forces. And we know that there have to be intermolecular forces, otherwise gases can never be cooled into a liquid. So, understanding states of matter, why something is a solid at a temperature, why at a particular temperature when something else is a liquid, when something else is a gas at that same temperature, all requires us to understand these intermolecular forces. We're going to see that intermolecular forces also helps us to understand solubility as well. So, if we come down to this picture on the next page, here we have 300 milliliter sample, which would be about a third of a quart. And it's liquid nitrogen, but when it evaporates, if we're able to capture it all, it would fill up a container of 200 liters. And that gives you a sense of how close together the particles are when they're a liquid and how far apart the particles of nitrogen gas, the molecules of nitrogen gas, end up when they enter the gaseous phase. Here's another example over here where we talk about benzene. We have liquid benzene, and then down here, and then we have solid benzene. And you'll notice that the heights in the container doesn't change much. There's not an awful lot of difference between the volume of a liquid and a volume of a solid. So, the molecules in a liquid are packed together and about as tightly as the molecules in the solid phase, therefore. In the solid phase, of course, more likely than not, they would pack together in a geometrical pattern or array that we would call a crystalline structure, though not all solids are crystalline, some are amorphous. And that will be a topic for the next chapter. So the key points. Number one, these intermolecular forces help us to understand melting point, boiling point, and helps us to be able to predict and then verify how much energy does it take to change phase. Number two, these intermolecular forces will help us to understand what will dissolve in what. You're going to hear that famous phrase, like dissolves like. Polar will dissolve in polar, nonpolar will dissolve in nonpolar. And we're always interested in structure. What is a three-dimensional structure? And this is especially true when it comes to DNA and proteins in biology. If you've already taken a biology course, or if you're taking one now, the subject of intermolecular forces is going to come up a lot, particularly a kind of intermolecular force that we'll get to later in the chapter called a hydrogen bond. So, first of all, when we talk about ionic compounds, which are made out of ions, which are positively and negatively charged particles. You memorized a bunch of ions way back when. And these are all governed by the electrostatic forces of attraction. If you remember Coulomb's law, force equals some proportionality constant times the one charge multiplied by the other charge that is nearby divided by the distance between them squared. That's the equation for Coulomb's law. So we can calculate this force of attraction if we know the values of these charges, whether they're +1 or +2 or -2, and then when you multiply by the quantity of a charge, which is equal to the charge of an electron. And then this is going to be the distance between them, and this is a constant that you would look up. So that's what we mean by electrostatic forces of attraction. And we can calculate those energies. And we see that for ionic bonds, it's about in the vicinity of 1,000, give or take a couple hundred kilojoules per mole. However, when we talk about a covalent bond as opposed to an ionic bond, covalent bonds are about half that or less than half of that, 100 to 400 kilojoules per mole. So intermolecular forces are generally less than about 15% of the values of the covalent bond energies. So we go from at the top of the chain are the ionic, and then we come down here to the covalent, and then we get down here to the very bottom. We have these intermolecular forces, and of course the intermolecular forces have a range from very weak to very strong as well. So when we look at just van der Waals forces and put ions aside, for just looking at molecules that are not charged particles, we have molecules that have a permanent dipole. Dipole means they have two poles. They have a distinct positive region and negative region. Sometimes we call them dipole-dipole forces between one molecule with its dipole and another molecule with its dipole. Sometimes we have attractions between a molecule that has a dipole, meaning it's polar, and a molecule that does not have a dipole. It's nonpolar. And we would call that also a dipole, meaning naturally occurring, versus induced dipole, meaning not naturally occurring due to its structure, but only occurring because of the way in which it moved around and got close to another particle or banged into the side of the container. It was temporarily induced. And then finally, the weakest, generally speaking, are the induced dipole. You can have substances that are made out of nonpolar molecules, but you can cool the temperature down until they become a liquid. So there's got to be forces between the particles. But it's going to be a pretty low temperature. And this would be induced dipole forces. Now, in order to think about what we mean by an induced dipole, let's suppose that this circle I'm drawing right now is a nucleus. And let's suppose that these dots all over the place are electrons moving around in their energy levels. Now let's suppose that as this particle with this blue nucleus moves around, let's suppose that just through sheer probability, every now and then, a couple of the particles on the right side happen to be over on the left side. You would have a temporary imbalance, a little bit more negative on the left, a little more positive by comparison on the right. That would be an induced dipole simply by the probability that as electrons move around, it's likely that on occasion some might be more on one side than the other. Another thing that could happen, of course, is if it bumps into a wall or if it comes close to a charged surface maybe, and that might repel electrons over to the other side. And now it definitely has a negative induced side, and by comparison, a positive side over there. If you rub a balloon on your shirt or in your hair, you brush electrons onto the balloon, and then when you take that balloon and you begin to approach the wall, the negative charges on the balloon repel the negative charges all along the wall, leaving behind a positive region of the wall and the negatively charged balloon, and they'll attract to each other and the balloon will stick to the wall. So we can talk about interactions between ions and molecules. We can talk about interactions between molecules and molecules, and the subcategory there would be, are those molecules polar or nonpolar? So you have lots of variability here. So when we say polar molecules, we mean they have a north pole and a south pole, though we usually talk about a positive pole and a negative pole. The Earth is polar, if you want to think about it like that, because it has a north pole where Santa is and a south pole where the penguins are. All right, and there are forces of attraction between positive and negative. The molecule itself may be polar, but its positive side might be attracted to the negative side of a different polar molecule. Now, here's Coulomb's law again. I already drew it for you. And here it is again. This time I give you the value of K, which is a very, very large value. It's rounded off to 9 billion Newton meter squared per Coulomb squared. But let's take a look at this chart up here. You can see that with lithium and then sodium, potassium, rubidium, we are going down the periodic table where the alkali metals are. Hydrogen would be up at the top. And as you go down the periodic table, obviously the radius gets bigger and bigger because you're adding energy levels. And as you go down the periodic table, your enthalpy of hydration, that is to say the energy that it would take to remove water molecules, gets less and less and less, because when those molecules are really far away from the nucleus, positive nucleus, compared to earlier, it's easier to take them away. It doesn't take as much energy. So again, looking at Coulomb's law, we know that distance is a factor. Inversely proportional, we know charge is a factor, directly proportional. And as far as dipole or molecules with a dipole are concerned, the magnitude of the dipole. The magnitude of that dipole is sometimes called the moment of the dipole, having nothing to do with time, like a moment in time. And that's measured in a unit called the debye, named after a chemist named Claude Debye. Now, you might remember doing a lab in first-year chemistry of hydrated ions, molecules that had water embedded, I shouldn't say molecules, crystalline structures that had water molecules embedded in their matrix. And then you masked a certain amount of that crystalline structure, and then you heated it up and drove the water off, and you masked it again, and you were able to find out the molar ratio of water molecules to the moles of your crystal. There's that word hydration again. So hydration here doesn't refer to hydrogen, it refers to water. So hydration is the enthalpy of solvation, not salvation, solvation. That is the enthalpy of dissolving in a solvent. And if that solvent is water, we have the more specific name of enthalpy of hydrogen. So if this circle represents enthalpies of solvation, then this circle, Venn diagram, would represent enthalpies of hydration as a subset of enthalpies of solvation. And we can measure those energy values. And you already saw table 12.1. And now let's take a look at figure 12.3 on the next page. Before we go there, though, I think you would be able to do this on your own pretty easily. And of course, you have to take into consider two things. When you're looking at sodium and cesium, you know that cesium is much farther down the periodic table than sodium, so it has more energy levels. It has a bigger D. But when you look at magnesium compared to sodium, sodium is right next to magnesium on the periodic table. Magnesium, of course, is a +2. Sodium is a +1. So here you're looking at Q. The charge is doubled, which is going to create a stronger force of attraction. And here's a diagram to kind of represent the enthalpy of hydration, where this is going to represent the attraction between a cation, potassium, and a water molecule that's polar over here. And it's separated by a certain distance d, which we can use X-ray diffraction to determine distances between the centers of particles and ions. You'll notice the sigma. You can have the positive and the negative regions. You could also just say positive where the hydrogens are and negative where the lone pairs and the oxygen are. And so here's your dipole moment, or your moment of the dipole. All right, let's come to section 12.3, interactions between molecules and dipoles. So we're going to leave the ions behind, and now we're going to be looking at dipoles. And your two dipoles, one molecule could be the same as the other, like if you had a whole bunch of water, or a whole bunch of ammonia, or the two molecules could be different, dissolved in each other. But if they're both polar, then you're going to have dipole-dipole interactions, or dipole-dipole forces of attraction, where the positive is going to be attracted to the negative right here. And that needs to happen significantly for a gas where your particles are spread out to become a liquid. And then to some extent, as the liquid becomes a solid, then you're crystallizing it. Down here, this should make sense. The greater the forces of attraction between the molecules in a liquid, the greater the energy that must be supplied to separate them. And of course, the more energy you have to supply, that's going to raise the melting point and raise the boiling point. So the stronger the polarity of the molecules, the higher will be the melting and the boiling points. And this statement repeats what I just said. The boiling point of a liquid depends on the intermolecular forces of attraction. You might recognize some of these salts, hydrated salts, in first-year chemistry. Maybe you used a blue crystalline substance called copper sulfate pentahydrate and you drove the water off. And your goal in the lab was to find that number 5, a ratio of 5 waters to 1 copper sulfate in the crystalline structure. And here's some of your hydrated salts. Now, later on, in chapter 22 of the book, we don't spend a whole lot of time there, unfortunately, because we run out of time. But we see that when, for example, with chromium 3 chloride hexahydrate, that really this formula is a little bit more accurate because it shows the chromium. It shows the chromium in the center, and then it shows 4 water molecules that are surrounding it. And then there are 2 chlorines, and then you've got 2 water molecules as a part of the matrix. So this second formula, which you would learn about in chapter 22, if you were focusing your attention on transition metal chemistry, is much more specific and detailed than what you learned in first-year chemistry. For our purposes, what you learned in first-year chemistry should be sufficient. And we can, of course, calculate how much energy it takes to go from a liquid to a vapor. And that's the same amount of energy that's going to be given up when you go from a vapor back to a liquid. So what do you have to do in order to boil water? You have to add heat. So it's endothermic. You're adding heat to turn a liquid into a vapor. What has to happen, therefore, when the vapor returns to a liquid? You have to lose that heat. That's going to be exothermic. Let's see. Solubility. Like dissolves like, and this goes both ways. Polar dissolves in polar, nonpolar dissolves in nonpolar. Polar will not dissolve in nonpolar, and nonpolar will not dissolve in polar. It's a good general rule. And of course, the word like is not like you might like something that's posted on Facebook or whatever. It means alike. Similar in the property of whether it's polar or not. Now, some things that can dissolve in each other can dissolve in any ratio you want. This is a vocabulary word from a few chapters ago. We say they are miscible in each other. Alcohol and water are miscible. They can dissolve in any proportion, 1 part water to 99 parts ethanol, or 99 points water to 1 point ethanol, part water. Ethanol, or anywhere in between. And you create a homogeneous mixture. You create a liquid that's perfectly blended together and you can't see any difference from the one liquid to the other. It's not like oil and water that don't dissolve in each other, and you can see the layering effect. Now, you'll notice something here, that as your molar mass gets bigger and bigger and bigger, that your boiling point gets bigger and bigger and bigger. In other words, it takes more and more energy to turn bromine into a gas than it does to take nitrogen into a gas. In fact, nitrogen is already a gas well before it ever gets to the coldest temperature on the planet, which is a good thing. And the reason for this is the bigger the molar mass, the more electrons you're going to have. And the more electrons you have, then think of a cloud of electrons as a general way of speaking about all of the electrons for all of the molecules of nitrogen or bromine or whatever. And all of those electrons, they're moving around, and the more electrons you have, the more of an imbalance you can have, the more of an induced dipole you can have. And the more and stronger of an induced dipole you have, the higher your boiling point is going to be. And the more energy it's going to take for this water of hydration. Now this is for nonpolar molecules. And here we're talking about an intermolecular force, which we'll get to a little bit later, called the London force, or the induced dipole force. ID also stands for intelligent design, of course. Anyway, for polar molecules, we see the same thing. Bigger the molar mass, the bigger the boiling point, the more energy it takes more energy for the energy of hydration. But the cloud of electrons is not going to be the sole reason for why you have this increase in boiling point. It will be especially due to the fact that these molecules are polar. Now, there's an extreme dipole-dipole, and it's so pronounced and it so does not fit the ordinary pattern, as you'll see in a minute, that we actually give it a special name. We call it a hydrogen bond. You've got to understand hydrogen bonds if you're going to understand biochemistry. And hydrogen bonds occur when you have one molecule that either has a nitrogen or an oxygen or a fluorine in it, and another molecule that might have one of those atoms but also has a hydrogen. And one of these connected to hydrogen is very small, and these are very electronegative. Nitrogen, oxygen, fluorine are very electronegative. So, and of course, they're all in that second row on the periodic table, so they're all very close to the nucleus. Chlorine is electronegative, but it's another energy level farther away from the nucleus. So when you have a connection between NOF, as I call it, and hydrogen, you have what we call a hydrogen bond, which is an inordinately large, doesn't fit the pattern force of attraction. Now, before we look at a very important graph, here's ethylene glycol, otherwise known as antifreeze, interspersing with the water molecules. And here is some hydrocarbons being mixed with, looks like motor oil. And you can see the layering effect here. One layer on top of the other layer. Doesn't dissolve. All right, let's look at this graph. And I'm going to start here with antimony tetrahydride. Now, if we go from right to left on the periodic table, and we're down here on row 5, antimony is element number 50. And we're going to go, we're going to go up the periodic table to the element above it, germanium, to the element above it, silicon, to the element above it, carbon. And we have this pretty nice pattern. And we're saying, yep, that makes sense as I go from a big atom. Remember, antimony is element number 50, so it has 50 protons and a lot of neutrons. Germanium is element 32. It has 32 protons and a bunch of neutrons. Silicon is element 14. Carbon is element number 6. So you can see that your dispersion interaction forces, otherwise known as London forces, otherwise known as induced dipole forces, as those forces get wimpier and wimpier and wimpier because the molar mass is going down, it takes less and less energy to turn it from the liquid to the vapor state, to boil it, in other words. So you say, okay, well, that makes sense. Let's pick another element. Let's take a look at the halogens. So if we look at the halogens, we're going to start off with hydrogen iodide. Again, we're down there on the 5th row. We'll go to the element above it, which is bromine. Yep, so far so good. It's a smaller molecule, so it should take less energy to boil it. Then we go to the element above it, which is chlorine. Yep, it takes even less. But then all of a sudden, when we go to the element above that, it jumps way up here. Instead of being down here, it's way up there. And that's because that's where you end up having a hydrogen bond. Fluorine, with its high electronegativity close to the nucleus, and very close to the hydrogen because it's a small atom. It's an unusually strong attraction, so it's going to take a lot more energy. And so you might say, okay, well, let's see if this pattern continues. Let's go to antimony. Antimony is element number 51, and the element above it is going to be arsenic, and the element above that is going to be phosphorus. So far, so good. It looks like it's going there, but all of a sudden, when we get down to the next element, which is nitrogen, it jumps way up there. Jumps way up there. Instead of being down here, it's way up there. Again, hydrogen bonding. And finally, we can confirm that with beginning with tellurium, element 52, element above it, selenium, element above it, sulfur, and we see that pattern, and then all of a sudden, way up here, there's water. Let's see the effect that hydrogen bonding has on the boiling point, and also see the effect that that hydrogen bond, which is so strong, is going to have on protein formation and the stability of proteins and the stability of the DNA molecule and so forth with all the hydrogen bonding in these biomolecules. And I've already talked about the difference in electronegativity. And here's your definition of hydrogen bonds. It's a super strong dipole-dipole involving NOF, nitrogen, oxygen, fluorine. And here it is again, down here. And here's all your different possible hydrogen bonds. You can have the hydrogen in a nitrogen-bearing molecule connected to another nitrogen, or connected to a molecule with oxygen, connecting to a molecule with fluorine. Or if you have a hydrogen connected to oxygen in a molecule, like in water, it could connect to nitrogen in another molecule or oxygen in another molecule, like another water molecule, or another molecule that has fluorine in it, and so forth. So reading over here, the hydrogen atom has an extraordinarily small radius. This means that the partial charge in the hydrogen atom is concentrated in a small volume. In other words, it has a very high charge density, the density of the charge. Not the density of the mass, but the density of the charge. And the effect of this hydrogen bonding is I'm going to be able to explain all kinds of different things, and I'm going to let you look at example 12.2, and you have to always look for that hydrogen bond right there to know that this is going to exacerbate or make greater the boiling point compared to if there wasn't a hydrogen bond present. And of course, the properties of water, if you want to talk about a molecule that looks simple, but is extraordinarily well designed. In other words, if you tweak the bond angle of 104.9 degrees a little bit, or do some other things, then water just doesn't have the properties we need it to have in order to do all the amazing things that it does. It's amazing in and of itself that we have so much water on the planet. It dictates the chemistry that's going to be involved, both on the planet but also in life. And it all has to do with water being a very, very polar molecule with strong hydrogen bonding. If you're walking down the street and you're accosted by Al-Qaeda and they ask you some question about bonding, More than, like on an AP test, more than likely the answer is hydrogen bonding. Now, I will say something, by the way, just came to me. Water also has induced dipole. But the induced dipole forces of attraction between water molecules due to the uneven distribution of the electrons is not worth considering compared to the strength of the hydrogen bonding. In other words, all molecules have induced dipole. Sometimes they're the only ones, in which case they're very important. Sometimes there are other ones that are more significant, in which case we ignore them. That's commonly missed on tests. All molecules are going to have induced dipole. They may or may not be significant. Now, the water molecule can make 4 hydrogen bonds. We come up here, and you can see the 4 hydrogen bonds represented by the dots, there, and there. And those hydrogen bonds force the water molecules into a crystalline structure. That crystalline structure is kind of open, which is why ice expands as it forms, and therefore ice floats, which is wonderful because if ice were to freeze and sink, like all other solids do when they go from liquid to solid, oceans and bodies of water would freeze from the bottom up and kill all the organisms that live in them. And of course, since most of our oxygen that we breathe comes from the phytoplankton in oceans, well, you would hate it when that happens, if the oceans froze over. All right, so you get that. You also get a 6-member hexagonal ring in that open structure, which accounts for the beautiful hexagonal structures of snowflakes. And you can see the different possible structural designs of snowflakes. There's over 30 of them that they've categorized now. They're really amazing and beautiful. God has a tendency to put both incredible design with incredible beauty into the same created thing. So we've already mentioned the snowflakes. The density is about 10% less when the water freezes, which is why ice floats. We should also mention the fact that when that cold water begins to get cold and approaches freezing, it also becomes denser than the warmer water at the bottom. And so the cold water sinks, the warmer water at the bottom comes to the surface. And so the cold water, remember cold water can hold more oxygen than warm water, just like a can of cold soda holds more carbon dioxide than a can of warm soda. And that means that the cold water sinks, bringing oxygen down to the bottom of the lake and the ocean, and all the nutrients that have settled at the bottom then come up to the surface, where a lot of the fish and so forth are. Here's an interesting graph. When we think about density increasing, obviously, as the temperature goes down, your density goes up, just as you might expect. But then between 0 and 4 degrees, instead of continuing on, those hydrogen bonds kick in, push the water molecules farther apart, and now my density actually goes down. And now my density is less than the density of water. And then once we have all ice, then we resume. Density increases just as it gets colder and colder. So it's only in this range of 0 to 4 degrees that water does something absolutely unique compared to all other liquids as they freeze. And that's important to understand that. Also, water helps to moderate temperature on the planet. It has an extraordinarily high heat capacity. It can absorb an awful lot of heat without its temperature changing a whole lot. If that were not true, the oceans would get way too hot around the equator. But the water around the equator absorbs a tremendous amount of heat, and as the Earth rotates, as the Earth spins on its axis, and as you have uneven heating on land versus water, you get these wind currents and water currents that help to carry the warm water down here towards the polar regions. And that means the polar regions aren't going to be as cold as they might otherwise be. And you all know that when you're near a large body of water in the hot summer, it's a little cooler there because the water temperature is less than the air temperature. But then at night, the water is going to be warmer than the cooler the cooler air over the land, because land has a low specific heat and water has a high specific heat. Now, by the way, the difference between heat capacity, which is measured in joules, and the specific heat, which is going to be a joule per gram Kelvin, specific heat is a value that is unique for every pure substance. And you look it up on a chart, you wouldn't have to memorize it. Here's another example. If we have a body of water right here, and we have the sun up here smiling at us during the daytime, the sun is going to heat up the land, and it's going to heat up the water, but the water is going to heat slowly because of its high specific heat, and the land is going to heat up very, very rapidly and be almost too hot to walk on the beach. So as a result, you have super hot air here, which begins to rise. And as that hot air rises, it's going to move in the direction of it doesn't mean you're going to end up suffocating if you're on the land here, because all the air is leaving you. It creates a breeze, because as the hot air rises, the cooler air over the lake or ocean flows, in this case, to the left to take its place, and you feel refreshed. So you have winds blowing towards you when you're on the beach during the daytime. Now, let's erase the sun. And now we have a moon. And now it's nighttime. And so at nighttime, the water is still pretty warm. So I'm going to erase this and try to erase that. And so what's going to happen now is the heat is going to rise off of the body of water, and therefore the cooler air from the land, which has already cooled down rapidly because of its low specific heat, will flow to take its place, and now you have a breeze blowing out to sea. And if you were on a little mattress here and weren't paying attention and fell asleep in the evening, you'd find yourself blowing out to sea, which happens periodically, and then you call for the Coast Guard. So you hate it when that happens.